Good morning, everybody. I go under the knife at about 1:30, so if you're trying to get rid of me, arrange for the power to go out right around then. I don't suffer any illusions that there are some of you that are kind of like, it would be nice if Mr. Balogh wasn't able to come back.
That's horrible. Who would say that? Yeah. Me.
Thank you, Drew. Right? As the giver of homework, I know I inflict pain on people. They're going to be burning nerves in my neck this afternoon. It feels like a reverse sunburn when you wake up, right? If you've ever had a sunburn, just try imagining, instead of it being the top layer of your skin, imagining being down deep and sort of like feeling it like radiate upward through all the layers of your skin. That's kind of what it feels like. Not really. It does nothing else. But what it does is it makes it so I can feel my fingers again. Positive. So, So modern medical science is pretty awesome. I'm always disappointed though. They never let me watch. I kind of want to watch. Actually, I'd love to do the procedure, but they won't let me do that either. So, no incisions. It's all needles. They'll put 6 needles in the right on either side of my spine, and then they will heat the needles up to 80 degrees Celsius for like 4 minutes, and that's enough to kind of burn away. They got to park it right over the tops of the nerves, and so they spend about 20 minutes with me awake, poking things. Right? And then they'll ask me like, lift your arm, or can you feel this? And they'll send electricity through it. And if I have any sensation, they're on the wrong nerve. It's important. It's actually pretty fascinating. Because they've hit the electricity and my whole shoulder and arm got to go, right? And they're like, no, that's not the right one. Tomorrow I won't be fit to be human, so you saw the announcement, right? Okay, so we're just going to ignore lab tomorrow. I know you're really disappointed. You're going to miss out on a whole lot of vectors. But we won't come back to that lab. We're just going to skip it. But I will be here on Thursday. I might be sitting down a lot, but I'll be here on Thursday. But we'll see. We'll see how it goes. All right. We're kind of almost halfway through this unit already. It's kind of scary, right? We've only done 1 chapter. There's only 3 chapters in this unit, right? But it's time to talk about circles. And it's a good intro. We're going to come back to circles later, too, okay? But we're going to take just a chapter here to talk about the forces involved in this motion and why it's important how we apply it to different things. So eventually, like on Thursday, we're going to be talking about planetary orbits, because that's what this is. I mean, I know this is a tennis ball on a string, right? But like, this is the orbit of the moon around the Earth and the Earth around the sun and the International Space Station, all that kind of stuff, okay? So there's some terminology here that can get kind of, confusing a little bit. What is the force, like with my tennis ball and string right here, what is the force that is keeping the ball going in a circle? Well, okay, so gravity just wants to do that, right? Okay, and that's not what's happening. Even if I kind of do a simple just rocket back and forth, because later, different chapter, we're going to learn that this is also a circle, okay? But like, gravity's causing it to kind of want to go down, right? But there's something that's keeping the ball from like falling, right? And in this case, okay, there's something that's keeping the ball going in a circle. Because if I let go of the string, what will the ball do? Okay, yeah, so I'm going to try, not always successful, I'm going to try to let go of the string when the ball is right here at the horizontal. Okay, let's see how well I do. I want you to know what direction it's going to go if I release it at the horizontal. You guys better duck. Okay. Which way did it go? Up, right? A little bit out because I didn't quite nail it, right? But it didn't go flying woo that way, right? Okay? In order for it to go that way, now you guys really duck. In order for it to go that way, what do I have to do? Let go where? At the bottom, right? Oh, too early. right? Okay, that one's harder. So what is again, back to the question, what is the force that's keeping the ball going in a circle? Okay, there's a name for it. Tension, right? Okay. The object causing that force is what? The string. So the string is exerting tension, right, on the ball. Okay. We give any force that causes something to go in a circle a new name. And it's called the centripetal force. That's a very fancy word for center seeking. It's like a Latin word, okay? Why do scientists and doctors, why are we so annoying and just use big words all the time? Because we're flexing. Actually, they've actually been showing that that's kind of true, right? You whip out big words to sound smart, okay? But there's another reason for the big words. Anybody know what it is? Specificity is a good reason. That's another fancy way of saying big words can be very accurate. You have to use a lot of easy words to describe what's going on in certain situations. That can be very quickly explained by using very specific words, right? So that word centripetal is one of those words. Instead of having to say, okay, it's the tension in the string that's causing this thing to go around in a circle, I can just say the ball is experiencing a centripetal force, right? It just sort of just tightens everything up. Now, is the centripetal force a new force? No. Remember, a force is a push or a pull, and you need to be able to define the object or state the object that's causing it. The tension in this string is centripetal while this thing is going in a circle. We're not adding a new force, we're just giving a new name to a force that's already there. So we need some circles, okay. Let's see, can I get it to cheat? All right. I'm just going to draw a coordinate system on this circle. No, we'll do that later. So let's say that the tennis ball is like right there, okay, and it's attached to its string, right? Which way would the tension be pointed? I just proved to you what happens, right, when I let go right here, right? Okay. It's an inwards force. It's pulling it into a circle, right? In fact, when I let go, inertia just means it's just going to go straight, right? Okay. But thank you for saying outwards. Name the object that is pulling this ball outwards. There's no normal force because it's not in contact with anything. Okay, technically in contact with a string, but we already said that one was tension, right? Okay. Acceleration is not a force or an object. Gravity is a force and only points down, doesn't point out. There is no object that is pulling this ball outwards.
There is no outward force.
And there is no outward force. Okay? Alice, what did you just say?
Outward force would be centrifugal.
Okay, that's a bad word in my class. It's okay, I asked you to say it, but from now on, we're not saying that, the C word anymore. Okay? I've done this before already, but we're going to do it again. Okay? Do you remember what happened when we accelerated the car last time? We hit the gas, and half of you said the force was that way. Okay? And I asked you for the object, and you're like, okay? Same thing's happening with the centrifugal. Sorry you had to hear that. Force. Okay? It's a fictitious force. It doesn't exist because there's no force, because there's no object that causes it. Let's go for a ride on the physics bus. This is a road. Top-down view, drone's eye view. Okay? And here's the physics bus. Okay? And the physics bus is negotiating this turn and turning to the right. Okay? I want all of you right now, so I'm driving the physics bus, okay? You're all in the physics bus, I'm driving the physics bus, right? I want all of you to move in the direction that you would move when I turn the bus to the right. Are you ready? Right? Okay, you all went left. Why? Because that's what happens, right? Mr. Baylor, that's exactly what right? Okay? And you get pulled to the outside of the turn. Name the object that is pulling you to the outside of the turn. The bus is actually doing the opposite. Which way is the bus pulling on you? To the right. How do you know? Because you're turning right. Okay? So the bus, right, and the seat and your seatbelt, whatever, okay, they're all pointing towards the inside of the turn. In this case, if we're turning right, then it points to the right. Everybody and their dog will swear that there's a force on them to the left. Name the object. There isn't one, okay? It's a fictitious force, and more accurately is described as your inertia coming into contact with a rotating coordinate system. Remember I said big words, right? Okay. The coordinate system of what's the bus doing? It's turning underneath you. What does Newton's first law say about what your body wants to do? Go in a straight line, right? So if your body continues in a straight line, but the bus turns underneath you to the right, what side of the bus is going to get in your way? The left side of the bus, right? And so because it's a coordinate system that is rotating and accelerating, we start inventing forces to try to explain what's going on from our coordinate system, our point of view, okay? So the centrifugal force is fictitious in that there's no true force. That doesn't stop, annoyingly, engineers from using it. Engineers will define centrifugal forces all day long, right? Because it is kind of a handy shortcut, right, for describing what's going on, even if it isn't real. And this is the one part where I'm like, engineers, you're not being consistent. You yell at me all the time for pretending things, right? And now here you are living one of the greatest lies of Newton's laws that there could be. So, how many forces keep this ball going in a circle? Just one. Okay? Which way does it point? Towards the center, or centripetally, if you want to sound smart too. Yeah?
If the force was pushing outwards, would it not stay in that general circle?
It wouldn't do a circle, right? Okay. I don't know. How do you get... This is what happens when you do outwards. Right? Okay? So, yeah. Kind of. Yeah, right. Okay. Pluto. We are going to talk about this on Thursday. It is not, and I will fight you. Okay? I have proof. Astronomers were idiots back then. Okay? Jury's still out now. But anyway, right? We'll get there. We'll get there. Okay. Here's some things that we know about this motion. So the force, right? So in this case with the ball on the string, it is tension pulling towards the center, but we refer to it as the centripetal force. Whatever you do, don't come in here and draw another one that says FC, right? That's not right, okay? Because there isn't another object pulling it towards the center. There's only one object pulling it towards the center. Is the ball accelerating?
Yes.
Even if I move it around at the most constant speed I can get it?
It's changing direction.
The speed isn't changing, but the direction is. It's constantly changing, isn't it? In fact, what direction is the ball going in the instant that it's horizontal like this? At this instant in its path, right here, which way is it going? It's going straight up. Okay? What about when it's at the top of its path? To the left. What about when I don't have shoulders anymore, right? Okay? So no matter where you are, the velocity of this object, how could we describe its velocity?
Circular.
It's not circular. It's tangential. It's at right angles to the force at every point, isn't it? Okay, Griffin.
So because it's in a circle and it's constant in constant acceleration, its points of like the 90-degree point, 0, 180 at 270, it's never going to have a 0 because it's in constant motion.
Right, the speed is the same. Okay, so like I could draw it right there, but like right here, this thing would be moving like that, right? Length of the vector stays the same, but the direction the vector is pointing is different, right? The direction this vector points at every point along the circle is different. And so therefore it is accelerating. Okay. The acceleration points towards the center also. Remember, Newton's second law says whatever direction your unbalanced force is, that's the direction of your acceleration. Just so happens that we can find that acceleration if we know the speed and the radius of the circle. So how do you make the acceleration bigger?
You make the circle bigger. Or smaller.
Smaller for the same speed, right? Okay. Or speed it up for the same size circle. One or the other. Okay. All right. So that's a toolbox equation. It's true. Notice it says a sub c, and that little c is there to remind us we're talking only about circular motion, only about a centripetal acceleration. This acceleration is towards the center, okay, following the force. Let's talk about a way to find out how fast something's going in a circle. Okay, back when we did. Do you remember this equation?
Nope.
No, you don't remember that equation? Do you remember that equation? Okay, right, okay. Let's talk about this one real quick, okay? We don't need a box. If we if we say the speed isn't changing, so I'm wiping out the acceleration here because the kinematic equations are not vector equations. Well, they kind of are, but like the acceleration exists because the direction is changing, right? Not because the object is speeding up or slowing down. We'll get there later. It's like chapter 10, okay? That leaves me with this statement right here. Distance equals velocity times time. So we can find that velocity. It's the distance divided by the time. How far does something go when it goes in a circle? It goes 360 degrees, which is not a really useful unit. For like degrees is not a velocity, right? It goes a distance, 2 pi r, in the time it takes to do a full circle, or the period. So there's another handy, if something is moving in a circle at constant speed, then I can tell you what that speed is if I know the radius of my circle and how long it takes for it to go around. The top box is an acceleration. So what units is it going to come out in if we use the right units? Meters per second squared. The bottom box is a velocity. And so if we use the correct units, what units is it going to come out in? Meters per second, right? So if they tell you it takes 3 minutes for a car to go around the track, you have to take those minutes and you have to put them in seconds, right? Put the distance in meters, so on and so forth, and you'll get the correct answers in the SI unit system. Just to round out just a few more things since we're on this page, even though it's going to come up a little bit later. I won't ask you if you remember Newton's second law because nobody wants to remember Newton's second law. What? Yeah, it's pretty easy to remember, but man, is it nasty, isn't it? Okay. Your book will also write this down. It'll say the centripetal force is equal to mv squared over r. I hesitate to put this one in a box because what just happened? Well, no, didn't they just take this and stick it in right there? That's what they did. Okay? So we'll put it in a dotted box because it's not really a new equation, right? It's just Newton's second law with centripetal acceleration put into it.
Can you just briefly do the breakdown of the letters and what they represent? The last one you just did.
Right here?
Yeah.
So that's centripetal force. Whatever force is pointing towards the center. In this example, I would put tension right there. Okay? M is mass. V, velocity. Technically speed, because it's just the value of velocity, right? But you can say velocity, it's just fine. And then what's this R? It's the radius of the circular motion, right? Does that help, Griffin? Thank you. You guys need to slow me down and say, Mr. Balogh, define these things. All right. So that's kind of, there's going to be a little bit more in this chapter, but those are we'll get them all in one spot, and now we're going to deal with a lot of the consequences. So if you're standing on the earth, are you moving? Yes, you are. Okay. I mean, we often treat the ground as the thing that's not moving, right? But in fact, it's rotating, right? The planet rotates on its axis. And so what we're going to do is we're going to try and figure out, and we're going to do it at the equator because that's where the rotation's the most and easiest to work out. We're going to try and find out what the centripetal acceleration of a person standing on the equator happens to be. By the way, as you go away from the equator and you go closer to the North or South Pole, what happens to that centripetal acceleration? Does it go up or down? Why does it go down? So, at Santa Claus's house, if you're standing outside the door, you're at the North Pole, what's going on? Right? Okay? You're not, your radius is effectively 0 at the North Pole. Right? The Earth's going around, right? But you're standing on the very top, right? The center of that rotation, right? So your effective radius is 0. Your radius when you're standing at the equator, right? You're whipping around, right? At the Earth's radius, essentially. Okay? So depending on where you are on the surface of the Earth, this number will be lower than what we're about to calculate. We're going to calculate the maximum. Okay? So they want centripetal acceleration, right? Well, we know that that's v squared over r. So we need to know the radius of the Earth. Everybody know the radius of the Earth?
Hold on, I have it.
Yeah, Google has it. No, it was 6,300 and something.
It is 6.37 times 10 to
Oh, it's pretty close. 6.37. Okay. So radius of the Earth, 6.37 times 10 to the 6 meters. All right, so we got the radius. That's easy. What about, okay, how do we find out how fast somebody on the equator is moving?
We guess.
No, we could do that. We could ask Google, or we could figure it out. Do we know any of this data? We know r, the radius of the Earth, right? Okay. So it's going to be 2 pi times the radius of the Earth. And how much time does this take?
24 hours.
Okay, right? So we know the period, right, in hours, right? So the period is 24 hours, but we can't put in hours, right? We don't want meters per hour. We want meters per second, don't we? So how do we take 24 hours and turn it into seconds? In 1 hour, there's 3,600 seconds. Don't guess, right? Just do chapter 1. What is this? Why do I not have this written down anywhere in my notes?
86,400.
Is it 86,400? That sounds right. That seems like a number that's stuck in my brain after all these years. Okay, it's a lot of them in a day. All right, so now we do 2 pi 6.37 times 10 to the 6 meters, all divided by 86,400. And like I said, I have it. Sometimes you just need to turn the page of your notes, and all will be revealed. I got 463 meters per second. I don't know what that is in miles per hour. Hey Siri, what's 463 meters per second in miles per hour? It said, I can use ChatGPT to find that answer. Oh, Apple. Oh my gosh. That right there is just like why Apple has just lost. Okay, meters per second in miles per hour. Like it didn't even think it is supposed to be getting better because they're about to update, like Google and Apple are doing the Vulkan mind meld. So Siri's going to become Gemini's voice, basically. Yeah, this is when the singularity starts. 1,035 miles an hour. So clicking along. That was a tangent we didn't need to go down. Okay, so now how do we find the centripetal acceleration? Square it, divide by the radius, and I got a huge 0.0337 meters per second squared, right? Right? So, and notice we aren't calculating the gravitational pull at the equator. We know what the acceleration due to gravity is at the equator. What is it? That wasn't a trick question. What's the acceleration due to gravity for all objects? 9.8 meters per second squared, right? So at the equator, the fact that you're at the equator, does it make very much difference about, like, does your weight change at the equator versus the North Pole? Not very much. 0.0377 as a factor of 9.8 is very, very tiny amount, but there nonetheless. Little story about me. I have a learning disability. I didn't know about it till college, and I was getting tested in college. And one of the things they did to test me was they gave me like a general knowledge quiz. And so I remember to this day this very question. The question was, why do people on the equator weigh more than people at the North Pole?
You said they don't.
Well, no. I paused. The poor bored graduate student that was giving me the test, right? Okay, was looking down at her notes, reading the questions, and I'd been asked all kinds of questions, general knowledge questions, and she was looking down. She wasn't paying attention, and I had been just rattling off answers or saying I don't know, and I paused when she asked that question, and she looked up, and I was just like, and she's like, what? And I said, do you really want to know the answer to that question? She's like, yes. I was like, no. Do you really want to know the answer to that question? And at this point, I'm sure she's like, where's that panic button? Like, you know, right? And she's like, she puts her notes down. She's like, what do you mean? And I said, because I can really answer that question. She's like, okay. And so she stopped me 5 minutes into the derivation of the angular dependence for acceleration based on your latitude on a sphere. And she's like, what major are you? And I was like, physics. She's like, oh. Makes a lot of sense. All right, let's do a quiz. Acceleration, and if there's an acceleration, there's a force, an unbalanced force somewhere, okay? So what we're going to do is we're going to go whoop-de-doo, wee! I don't know. It was a generic picture I took off the internet and failed to put down the source for. Yeah, no, I'm failed. It's not AI. It's too old for that. I've had this picture for like 15 years. I bet you it came out of a textbook. So I can probably name the textbook. Anyway, So we're going to do loop-de-loop. We're going to do roller coaster, loop-de-loop. You can do this in an airplane, whatever, right? But the whole essence of this thing, and we're going to, even though it's not pictured, we'll get to this in a minute. Even though it's not pictured this way, we are going to assume that this is a perfectly circular loop-de-loop. Okay? All right. So let's see. Can I make this thing? Oh, I can. Oh, that's fun. Okay. Old people learning technology is so cute to watch sometimes, isn't it? Okay. We are going to analyze this circle from at the bottom and the top. Okay? So we'll start at the bottom. And by analyze, I mean we're going to pull out everything we know about Newton's second law. There's going to be free body diagrams. There's going to be math. It's going to be vectors. We're going to use all these tools that we've been developing. Okay? So we're going to put the roller coaster down here at the bottom of its track. And then what question are we going to ask to get dug in here? No. What? Okay, you can start with forces, but I'd prefer objects. Right? You can do it either way. You can identify forces as long as you can name an object for that force. But I'd actually just prefer for you to start thinking about what's pushing or pulling on the roller coaster car. That's like the better way. That'll pay dividends in chapter 12. You do realize that everything I tell you is for a reason? And that reason isn't torture? Right? What's one thing that I know? That was a loaded question. I know what's coming. And I'm trying to prepare you for what's coming, right? So that's why I constantly try to remind you. I know you can do forces, but do objects instead, right? Like it's going to help you when we finally get to some other things where forces aren't going to save you. Okay, so what objects are pushing or pulling on the car? The track. Okay, what would we name that force?
Circular.
Oh, friction. We're not going to do friction. Normal force. Okay. We won't do friction just because it complicates it and doesn't do anything for us in this situation. There is friction there, but we'll balance it with a propulsive force and that'll be enough. All right, any other objects pushing or pulling on the car? Good, the earth, which is going to be gravity. Okay. Those are not equal. I know that they're not equal because there is an unbalanced force on this cart. And how do I know there's an unbalanced force? It's going in a circle, right? So, do I draw the centripetal force right here? No. What object is causing the centripetal force? The track. And we've already given the track force a name, the normal force, right? Okay. So the normal force is the centripetal force, right? Again, don't fall into that trap of just putting another force down. Centripetal is just another name for a force that's already there. You could if you want, or you could just not label it N, you just call it FC. I don't care. It's just a label, whatever works for you. Right? Your book would call it F sub n, I think. Okay. Okay. Are there any other objects pushing or pulling on this car?
The wheels.
It's part of the car.
Along the track.
Yeah, we were mentioning like propulsive forces and friction. I don't want to do anything in the horizontal plane.
The chains.
Again, part of the track. No, like you guys are coming up with great ideas, but they're not. I mean, we lump like the rider and the cart and everything are all sort of lumped together, right? Okay, and you're like, well, what about the other one in front that's tugging on it from like there's one right here and they're tugging. Okay, yes, fine, but let's just isolate the one car. Just keep our life simple, right? Okay. Are any of these? Let me put it to you another way. Is friction or propulsive force or any of the chains connecting it, are any of those forces pointing towards the center? No. So I don't care what they're doing, right? Okay. I want to analyze like the circular nature of this motion. Okay. So we're going to keep it going at constant speed, which means any horizontal forces have to be balanced, therefore they add up to 0, therefore I don't care. Okay? So which way is the acceleration? Towards the center. And what direction is towards the center when we're at the bottom of the circle? It's upwards, right? So again, I'm not going to draw this as attached to my free body. I'm just going to put it there to remind myself that that's the direction I'm choosing for the acceleration. So with that acceleration in place, or at least a guess for what direction the acceleration is, how do I complete my free body diagram? Coordinate system. Which way are we going to put positive y? Upwards. Why am I not putting positive x? Because I don't care, right? All right, so at the bottom, how would I write down Newton's second law? Start me out. What do I write first? What's the template? You don't know squat. You have no idea what physics is going on. What do you write down as the template? Ma equals. That's how Newton's second law starts. Okay? What goes on the other side of the equal sign? Forces, right? How many forces are there in the y direction? 2. Okay? They are normal force and acceleration is not a force. Gravity, the weight. Okay? Remember, leave a space. What do we do now? Put the signs on it, right? Normal, positive or negative? Mg down, so it gets negative. Again, it's a step-by-step process. You can make mistakes on the signs. You can make mistakes and put too many forces in or leave forces out. Like those are all legit mistakes to make, but you don't have to sit there and guess. You can write Ma equals and then forces in the y direction. You can write Ma equals and forces in the x direction. Like it's a process that you will mess up on, and that's okay. Make all the mistakes now, right? So that you get used to the process. Process is key. Okay. That's the bottom. Let's leave the bottom for now. Let's go to the top. So now we're upside down up here at the top. Okay. What's pushing or pulling on the car? Gravity. Thank you for naming the object. The track. So what are we going to give the track's force? What are we going to call it? The normal force. Which way does it point?
Down.
It points down. Why does it point down? It's not it's a centripetal force, because gravity is now a centripetal force. Why does it point down? We've gone upside down. The surface of contact, right, between the car and the track is right here, but the track can only do what? Push it down. Right? It's got to be perpendicular to the surface of contact. We said perpendicular surface of contact at the bottom was up. So as we go around the loop-de-loop, right, the normal force does have to point inward at all times.
So are we saying that it's, regardless of the position that we're in, it's always going to face towards the middle, but does that mean it's still going to be in the positive direction because we...
Good question, right? So maybe you don't believe me, but you just have to trust me. The normal force does point down. Some of you are like, Mr. Balogh, there's just safety things that hold on. This is an unsafe roller coaster. Which way is the acceleration pointed?
What acceleration?
It's inwards. And which way is inwards when we're at the top? It's down. It's centripetal. It's center seeking. Wherever we are on this circle, it has to point towards the middle, right? Okay, so if we're at the top, the centripetal acceleration is pointed down. So which way are we going to make positive?
Neither.
Down. Follow the acceleration. So when we do this at the top now, and we write Ma equals, we still have a normal force, we still have a weight, That didn't change. What changed was the directions things are pointed. Positive or negative for the n? Positive. It's okay, Griffin. Strong and wrong. Why is the normal force positive? Because we define down as positive at the top because that's the direction the acceleration was going.
Can you say before just move your head, for example?
Yep. I want to see you standing on your head. I want pictures on TikTok of you standing on your head doing your physics homework. No. Yeah, I wouldn't either. All right. And I don't. Okay. Wait, whoa, I made a mistake. I'm glad I have you guys catch my mistakes.
Can you explain why?
Which way does it point? Which way is down? Down is not up. Which way is down? It's positive y. So anything pointing down, if we're talking about the top of the loop-de-loop, the positive direction is down, which I know you're uncomfortable with. Get over it. Follow the direction of the acceleration. That's where you are going to be safe. I know it feels weird now, okay? You probably don't want to know this, but I'm going to show you how this can mess up if you insist that up is positive. Are you ready? Okay. If up were positive, okay, and you start your template and you write MA equals, and you write minus N minus MG, is this equation the same as this one? No. Because something is wrong. The negative N is correct, the negative MG is correct, but what's not correct? The acceleration direction is incorrect. Because if we say up is positive, what do we have to do? We have to make that negative MA. In my experience, in my career, and in my expertise, what I just showed you is actually harder to put in your head and easier to make a mistake on than if I teach you, no, make everything be down, be positive, just write MA equals, and then sort out the directions over here.
So if we are referring back to the positive or negative mg, if we can determine that in the down direction, y is positive,
Mhm.
anything that follows in that direction.
Has to be positive.
Okay.
Yeah.
Thank you.
That's what we call being consistent in physics. Pick something, stick with it. And if you pick up as positive, if that's the universe you want to live in, then to be consistent, you have to put a negative sign on the MA, and then your N, and then your MG, and then you will have exactly the same equation that's sitting right there. Because you can just multiply through by a negative sign, and boom, it's the same thing, right? Okay. Pick your poison. But a lot of physics textbooks and physics teachers, we don't deal with negative directions of accelerations. We align the direction we're calling positive with the acceleration. It just saves a little bit of mental forgetting when it comes to minus signs. All right. Maybe we should have taught kinematics at the very beginning as down is positive, because that's the way gravity. You guys would have killed us. You would have killed us.
Did we do that?
No, we didn't. Okay. We got to start somewhere, and that's where we started. Are these two equations, the red one and the green one, the same?
Perchance.
No. No, they're not. And we're going to solve for something weird. We're going to solve for the normal force in both cases. The normal force down here is MA plus MG. The normal force up here is MA minus MG. What's happening to the normal force as a rider goes around a loop-de-loop in a roller coaster? Does it stay constant or does it change? It changes. Where is it the most? At the bottom where it says plus, right? Where is it the least? At the top, where it says minus. What the heck is going on here? First of all, does gravity change whether you're at the top or bottom of the loop-de-loop? No, gravity, right? Earth's just going to pull on you equally, right? So gravity's not doing a thing, okay? MA, we can write this. We could, because we know it's going in a circle, we can substitute in the centripetal acceleration for the speed squared divided by r. That was on the other slide, right? Okay. I can do the same thing up here. But that still doesn't change the fact that at the top, the normal force is reduced. It's smaller than when it is at the bottom. In fact, a rider on this roller coaster will feel, okay, first of all, how would a rider feel their own weight? Look at the red. Look at the bottom equation. How would a rider feel their weight?
Because they're being pushed up by the cart.
In order for them to feel their weight, they would just need to feel mg, right? Okay? When you step on a scale in your bathroom and go step on the scale, right? What is the scale telling you? How much it's pushing on you. It's the only thing it can tell you, right? Does the scale know anything about what the Earth is doing to you? No, the scale can only know. You are applying a force to it. It applies a force to you. That's Newton's third law. And the scale reads and tells you what that force is. If your bathroom is not accelerating, kind of depends on what you had last night, right? Okay. But if your bathroom is a normal bathroom and is not accelerating, and this term goes to 0, like you're not going in a circle at speed, right? Then your normal force will be equal to your weight, right? But if your bathroom is accelerating, or to put it differently, you're sitting in a roller coaster car that is accelerating and going in a loop-de-loop in a circle, at the bottom in red, because you have speed and you have a radius of a turn, okay, what will you experience? A greater normal force. And in your brain's not going to go, oh, greater normal force because of centripetal forces. It will say, I feel heavier. You experience this every time you ride an elevator. We got one in this building, right? Go into the elevator, you push the button, what happens? Door closes, and all of a sudden you gain weight. So strong, right? Do you feel that like weight gain? It was that Pop-Tart you had for breakfast. Not good. And then as the cart comes to the floor that you're trying to arrive at, what happens then? Pop-Tart gone. Did gravity change its pull? No. What changed? You accelerated upwards to get to the next floor, right? And then you slowed down, decelerated to stop at the floor. But if you ask people, they'll say, oh, my weight changed. Your weight didn't change. You were pushed on by the floor more, right? You had to get going upwards, so the normal force had to increase. We call this apparent weight. It's this idea that people will report that they feel heavier or lighter depending on the normal force that they are experiencing. And in a loop-de-loop, that normal force changes. It's bigger at the bottom of the loop, and it's weaker at the top of the loop. And why are roller coasters fun?
Thrill.
Because some people feel like throwing up is a good time. Right? So, but what's the sensation of that loop-de-loop that we go, wow-wee, this is so cool? It's that feeling of being pushed into the seat and then, oh, I'm floating. Right? Okay? it's those changes in that normal force that are being applied to the rider that gives that sensation of, woo, this is fun. What speed is the minimum speed in order to successfully do the loop-de-loop? Is there a speed that's so slow that would cause the cart to fall off the track, assuming there is no safety mechanism to keep it on the track? What would the cart have to do? Think of it going around in the loop-de-loop, right? Can you imagine what the car would have to do in order to fall off the track? It would have to get too slow, right? Okay. What disappears if the cart gets going too slow? Hint, it's not gravity. Drew, what was it? It's the normal force, right? We want to solve for the condition where the track is no longer pushing on the car. Because if the track is no longer pushing on the car, they're not connected. And the cart is now what?
Falling.
In free fall.
And there will be death.
Hopefully not. If the normal force goes to 0 at the top, can the normal force go to 0 at the bottom?
No.
Mathematically, it cannot. We can set the speed to 0, but we still have weight, right? Normal force equals weight. Is it possible for it to go to 0 up here? Yeah, these two things, right, can cancel each other out. So if the normal force is 0 at the top, then we have 0 equals mv squared over r minus mg. We're going to rearrange. Okay, we're going to move mv squared over the other, multiply through by a negative sign. What's the same on both sides? So it doesn't matter how big or small the rider is. Why does it say you must be this tall in order to ride this ride? It's the safety restraint system that keeps the passenger attached to the vehicle, right? But in terms of the rider's mass, this makes absolutely no difference. Okay. And then I solve for what remains. It's the square root of r times g. That right there is the minimum speed that a roller coaster would have to have in order for it to stay on the track. Assuming there was no safety mechanism, no way to keep the car attached to the track, right? Which all roller coasters that invert have this. They have wheels on the top of the track as well as the bottom. There's like sets of wheels that wrap around the bar so that when the cart inverts itself, right, there's something that's still attaching it to the track. And so in a situation, emerging situation where they have to stop the cars from moving and people are on the upside down part of the track, they're still held on to the track. It's like clamped on, okay? And it sucks to have to hang there for a while till the rescuers can come and get you, but it's better than falling out, okay? But the thing in the box there is the minimum speed required for the cart to not get stuck in the loop-de-loop, for it to not come off the track if there was no safety mechanism. Okay, why is this one that I got in the picture, why is it not a circle? Actually, you can. There's several roller coasters that have near perfect circles in them. Disneyland's Mickey Mouse roller coaster in the California Adventures is one with a perfect circle. Is it the Incredibles one now? This is how old I am. So it's the one that's next to the lake in California. Yeah, okay. Yeah, it's still pretty much a perfect circle. Marriott's Great America, it's Six Flags over in San Jose. It's got one. Do they still have it where you ride it forwards and then you ride it backwards? Yeah? That's a near perfect circle.
They have to take G-force into account.
Yeah, kind of. Okay, they're doing two tricks here and it's really quite clever. By lengthening out the curve up here. So what's happening is this radius is like changing, right? So it's getting smaller down here and it's getting bigger across the top. By playing around, by making it this sort of teardrop or water droplet shape, this point, this speed right here, means that you only become weightless at a very specific point, the very top of the loop-de-loop. By making it teardrop shape, they can extend the zone up here where you don't need normal force. And you can feel that kind of weightlessness in the restraints. That feeling, if you've ever been in upside down a roller coaster where you like feel kind of like lifted up off the seat, and you're, right? Apparently that's fun, right? I've been on all sorts of roller coasters. I think they're fun, but I also think they hurt my neck and my back. So they will play with. The other thing that this does, right, is it lightens up that feeling at the bottom of being compressed and pushed into your seat. Roller coaster riders report over and over again that they like the feeling of like weightlessness. What they don't enjoy is being squeezed into the seat. And so this particular ride is trying to make the entry and exit of the loop like smooth and feel nice, right? If it's more of a perfect circle, you feel more of that. So, yeah, lots of engineering that goes into roller coasters. I was looking for pictures to try to explain what was going on with a banked turn, and I found this bus one, and I had to put it in. Like, if mass transit were this, sign me up. Right? Okay? This is obviously, this bus is in motion, right? Okay? No, it better be. Because if it's not, what's going to happen? It's going to fall, right? Okay? But this bus is going at like 50, 60 miles an hour on this test track. This is a test track in Germany. This is a Mercedes-Benz bus. Okay? And it's going around this test track, and it's not falling over. So this is an extreme example of a banked turn. Right now the Olympics are going on. It's like the only sports I ever watch, right? And they've got the bobsledders and the luge and all that kind of stuff, and they get up on those turns, right? Okay? And it's these extremely banked turns, okay? And they don't, if they're careful, they don't fly out of the turn, right? Even though there's very little friction in that turn, they can stay in the turn. So what I want to do now is I want to do the physics of bobsledding or testing buses, or why, if you go up in the mountains, you'll experience these banked turns, right, as we go places. Was there a hand out there? I thought I saw.
Yeah, but I think we're going to answer it.
We're going to answer it? Okay. Okay. So let's do the bank turn, okay, with no friction. I've got to... I don't have a blank for this one. Why don't I have a blank for this one?
Open up paint.
Yeah. I'm just going to use this. My export to PDF skipped a page. All right. So, it's going to work? Yep. Let's, first of all, what does a banked turn look like? Like, physically? Yeah, I mean, it's kind of hard to imagine the circle this car is. It's like kind of doing a circle. I tried to draw that sort of in 3D, right? Where there's like a slope. Ah, it looks like a hill. Yeah, it's physics hill, right? Okay, so that's what we're going to draw, right? We're going to draw the cross section of the hill. No. We're going to draw a triangle, and we're going to put a car on it, okay, and we're going to exaggerate the banking angle. We usually don't do it this steep, unless, of course, you are a bus. In this picture, and this is kind of hard to imagine, this car is driving out of the screen at us. Does everybody see it? The circle that this car drives in is... like, it basically looks like that. We're looking at a circle edge on. Like, top view, the car would be going around in a circle, right? Okay? But we're looking at this car from, like, the side view. So it's going around. It comes out of the screen the way we've drawn it, comes across, and then goes back in. It's going around. The circle this car goes in is horizontal. The bus is going around in a horizontal circle, okay? This car, again, it's going around in a horizontal. Even though the road is angled, the circle itself is nice and flat and horizontal. So If you really need to, you can put there's the headlights, and there's the surprised face upside down. We better take those out. Circle, right?
You just draw like a.
Yeah, but it's going to get messy. I don't like messy. I suck at drawing.
I was more thinking like a straight line and just kind of circles.
Yeah, it still is going to get in my way. Because what goes on a free body diagram? Forces, right? I want to make sure my free body diagram is telling me about forces that are happening. Name, we'll do it your way. Name a force. Earth. Good, you started with the object. I love it. Okay, so gravity. Normal force.
Acceleration.
That's not an object or a force.
Bank term. No, that doesn't accelerate.
Only two
We've finished all the objects, haven't we? The normal force comes from the road, and the mg comes from the earth. Are there any other objects? No. We're going to do frictionless, so the bobsledder, or you hit a patch of ice on this curved road. Okay. So, what direction does the acceleration point? Towards the center of the circle. Which way is the center of the circle?
That way.
It's perfectly horizontal. Which way are we going to call positive x?
That way.
Not up. You guys would fillet me if I said up. We have to put positive x in the same direction as the acceleration. So it's going to be perfectly horizontal. And some of you are like, finally it's back. Okay, so which way is positive y? We'll call that one up. Great. Okay. So we've set up our free body diagram. We're good to go?
Yes.
Okay. So we've got Newton's second law. We have to do it in the x direction and we have to do it in the y direction because there are two directions here, aren't they? Okay. So we're going to do max equals may equals. Again, it's kind of like my template, right? I can set this up without even thinking about it. And then now I've got to find some of these forces. Anybody see the problem?
We have to split it into components.
N has components. If you flip back in your notes and you see what we did with the hill the last time, we tilted our coordinate system, again, because acceleration was like in the plane of the hill. And that forced us to find components of gravity. Well, now, the coordinate system isn't tilted, right? So if I come in here and I visualize my coordinate system, just lay it right down on top of my object here, which of my two forces, mg or n, has no components? It's mg. Well, it has one component. It's all y, isn't it? Okay. So since we figured that out, let's go ahead and list it over here. Okay. But n does not live in just x or just y.
So make it both x and y.
So we have to find its parts. Oops. The part of n that points up and the part of n that points to the right. How do I know it has to point up and to the right?
X and y.
Because n points up and to the right, doesn't it? Right? It's pointing into the first quadrant, so it has to be up and to the right. Okay. Where's theta?
Rotate the triangle.
Down there.
Well, yeah, it's down there. But where is it up here, where I need it, where I need to find components? I'm going to leave you on a cliffhanger. Should I not tell you where theta is right now? Should I leave it on that cliffhanger?
It's against the y-axis, isn't it?
Yeah, it's up here. No cliffhangers.
Why is it up there?
A line that bisects two parallel lines has alternate interior angles that are equal. Okay, so the one that's sitting below, the angle that's sitting below here is theta. This right here is 90 minus theta, 90 minus 90 minus theta, which gets you to the angle that's up here. It's very similar to that second problem I made you do in the first lab. Okay? You can just trust me that the angle's up there. So, what does that mean for the vertical component? It's cosine. Why is it cosine? It's touching the angle, right? So this one's going to be n sine theta. We will pick this up on Thursday. I'll complete this, and then we're going to do some orbital mechanics, and we'll be done with chapter 5. Remember, we are not meeting tomorrow for lab, right? No lab. You get a day off. Finish your homework. Get caught up on some other classes, whatever you need to do. I'll see you on the other side. See you on Thursday.